Thanking a round of applause. Okay, and with that, let's start with our first talk. So the first talk would be given by Leo Lee from UT Austin, and he's going to tell us about the hierarchy of superconductivity and charge density wave orders. Leo, I'm going to give you a warning 5 minutes before the question time. Okay, please.
Do I have 45 minutes?
I think you have 40 plus 10, right? Yeah, 40 plus 10.
Okay, thank you for the introduction, and thanks for the organizer for the invitation. I wish I could be there in person, but it's a shame that I couldn't. I do appreciate the camera view of the venue, so it feels like I'm almost there. Right, so I want to talk about a hierarchy of unconventional superconductivity and the charge density wave order. And the actual experiment I'm doing is some form of angle result transform measurement in rhombohedral hexalayer graphene. Okay, so let me quickly go over the outline, right? I'll give a fairly brief introduction of the two concepts, unconventional superconductivity and electronic solid phases. And then I'll spend most of the talk talking about rhombohedral hexalayer graphene, and how we can use transform measurement to identify different type of CDW orders, and this very interesting observation that CDW order have their corresponding superconducting phases. Okay, so let's take a step back to go to the first unconventional superconductor. Right, I think this is still the best understood unconventional superconductor P wave in helium-3 superfluid. The low temperature phase diagram look like something like this. At about 2 millikelvin and with a large hydrostatic pressure, helium-3 condensing to a superfluid phase, and there are two different phases. The A phase is particularly interesting because one, it's an equal spin pairing, spin up, up, and down, down. Two, the Cooper pair has a finite non-zero angular momentum, right? There's a L vector, it points along the direction where the energy gap develop a nodal point. And this is called a chiral ABM state, right? The best understood P wave equal spin pairing state that we know. So what are the signatures that make this, that allow us to know that this is definitely an unconventional superconductor? There are two very early identification. The first thing is that if you look at the phase space of the helium-3 A phase, at zero magnetic field, you occupy a very small area at the high pressure, high temperature corner of the phase space. But once you turn on the internal magnetic field, you see that this polycritical points start to move down, meaning that the A phase become more stable. When you turn on the magnetic field, that makes this superconductor phase more stable. And if you keep increasing the magnetic field at about 5-6 kilogauss, right, the entire phase space is taken over by this A phase. So it is a superconducting phase that's favored by an external magnetic field. That's the first indication. And what I'm citing here is one is John Wheatley's review article, and one of them is David Lee's article when he won the Nobel Prize, right? So these are one of the some of the early discoveries that already told us helium-3A is a fairly non-trivial phase. The really definitive identification of the non-trivial, the unconventional nature comes rather recently, about 12 years ago. We've now known that because of the non-zero orbital angular momentum of the Cooper pair, helium-3 superfluid A phase is a superconductor plus a orbital ferromagnet, right? That means that it's switchable. You can control it with the external magnetic field. So people design this experiment. They have a sheet of pseudo 2D confinement for the helium-3A phase so that the orbital angular momentum is pointing out of plane, right? Either pointing up or down. And so you can use a magnetic field to train this orbital angular momentum. And when you take away the magnetic field, there still will be a magnet force because there's because of this magnetization of the superfluid itself. So when you move a helium-3 bubble on this 2D plane, right, you will feel the Lorentz force and bend leftwards or rightwards. So this is exactly the experiment they did. They cool down through the A phase, and then depending on how they train the orbital magnetic moment, they can see the deflection in the electron either upwards or downwards. Right. This is so some type of magnetic field driven switching is the most direct evidence people did to confirm that helium-3 A phase is a orbital ferromagnet, hence chiral superfluid. Okay, so this is what happened very early on in helium-3, and for decades people have been trying to study potential unconventional superconductor in solid state materials, and the progress here is a lot slower. For many years, we're searching for superconductivity that could be stabilized against a large magnetic field, right? Superconductivity usually want to live near zero field. And we actually, as a community, made quite a lot of progress. For example, this work that's done in uranium telluride 2, this superconductor itself is robust against a fairly large magnetic field, but there's a corner of the phase space where there's a reentrant superconductivity that's stabilized by a large magnetic field, so this raised a lot of intense effort trying to understand what exactly is the pairing symmetry. Is it P wave? Is it D wave? I'm not in this community, but from what I heard, that there's still some ongoing debate. There's still some effort trying to identify this. But in the direction of searching for unconventional, potentially P wave superconductor, some progress are made recently in multilayer graphene materials. This work came out from Long's group at MIT, I think about a year ago. And they have two outstanding observations. One of them is that there is this one superconducting phase that seems to be fairly unique in the sense that it's robust against a very large outer plane magnetic field. For other 2D superconductor, because of 2D nature, it's usually suppressed by an outer plane magnetic field of 0.1 Tesla, right? That gives you a sense of a comparison. But this one, despite the fact that the TC is extremely low, it's very stable against up to 2 Tesla of outer plane magnetic field. So that itself is showing something that there's something different here. But most remarkably, they also show this response that if you park in the superconducting state and start to sweep the outer plane magnetic field back and forth, there are these very distinct or very sharply defined transitions where the resistance peak, right? And this transition is hysteresis, meaning that there are on two sides of the transition, there's different type of superconductor. So their understanding is that the superconductor comes from a value polarized normal state, and this transition you're seeing is the transition in the underlying value polarization, right? So this is already very close to what we have seen in helium-3 superfluid, and that's why they call this signature of chiral superconductivity. Okay, right, and this is their understanding. The peak they're seeing is when the domain boundary is sitting right between two voltage probe, right, and there's a finite voltage drop across the domain boundary, and that allows you to see this transition as a peak in resistance. Okay, so as I'm talking about this group of material, I'm sure you have heard a lot about rhombohedral graphene. As we start to discover these interesting superconducting phase, there's something else that's happening at the same time, which is it looks like there's an abundance of electron solid state. This is also a paper that came from Long's group earlier, actually last year. It came out earlier this year. And what they see is that there's this branch in the phase space, a very large displacement field. This is actually a similar branch compared to where the superconducting phase comes from. The only difference is that in this sample, there's there's alignment between graphene and the underlying HBN substrate. when they do a line cut across here, they see quantum anomalous Hall effect and quantum anomalous Hall effect at integer filling, as well as reentrant quantum anomalous Hall effect at fractional filling, right? And so this is very reminiscent to what people have seen in quantum Hall systems at higher Landau level filling, where between two integer Landau level filling, there's a number of these re-entering quantum Hall plateau where the Hall resistance re-enters into the integer plateau, despite the fact that we're at partial filling of a Landau level. This has been studied very extensively for the last decades, and most remarkably, a lot of these are predicted before the experimental discovery, and so the understanding here is that there's some kind of electron bubble phase, right? Due to the Coulomb interaction and the unique feature of the Landau level, the wave function, electron, it's actually energetically favorable for electron to form these insulating island. Overall, it's a bubble-like charge density wave structure. At the same time, more recently, there's another work that came out from Shanghai Jiao Tong University, Ting-Xin Li's group, where they discovered this very interesting superconducting phase that sits right next to a reentrant quantum anomalous Hall insulator, as well as a fractional quantum anomalous Hall insulator, right? So this brings quite a few very interesting concepts together, fractionalized electronic charge, as well as electronic solid phase next to a superconductor. So I believe that there's still a lot of activity going on here, trying to figure out exactly what kind of superconductor this is. But suffice to say that there are lots of interesting activity in the community that involve the concept of unconventional superconductor and electron solid. Just for completeness, before I go into more data, let me just show that this is the original proposal by these authors, Boris Shklovsky. And their understanding is that if you take into account of Coulomb interaction in the Landau level, there could be quite a few different type of electronic solid. Apart from the bubble. Yeah.
Sorry, can you go back to the previous slide, please? So I think we should not mix the platforms. This is a different platform than MOT2, right? Than rhombohedral. This is MOT2, right?
Yes. Yes.
So there's a lot of ideas and work around what's happening to Moiré in rhombohedral. So we shouldn't mix the platforms, right? Rhombohedral with Moiré, you see Chern insulators and fractional Chern insulators. Rhombohedral without Moiré, you see superconductivity and none of the others. This is MOT2. It's a very different system, right?
Yes. Okay. I'm just mentioning in general that, yes, you're right. I thought I mentioned the twisted TMD, but maybe I probably forgot. But in a different Moiré system, superconductivity is observed to appear right next to a reentrant quantum anomalous Hall insulator. And it's interesting because a unconventional superconductor is being associated with the electron solid. And what is the connection there? We don't know, or I don't know. Okay. Right, so just want to mention that apart from the bubble phase, there's also a stripe phase that was predicted in quantum Hall effect systems, and this was later on observed at the Landau level filling 9.5, 11.5, or the higher filling Landau level seem to show this stripe signature. And the way they measure this is to do transfer measurement across a van der Pol geometry where you can flow current in two orthogonal directions, right? Depending on the direction of current flow, the transport response is highly anisotropic. And I think the figure of merit they have is that the resistance ratio they can get up to either 3,000 or 30,000. But if you calculate the intrinsic anisotropy in the conductivity, it's on the order of 20 to 30. Because resistance measurement tend to enhance the ratio to be larger than the actual intrinsic anisotropy. Okay, so let's go to rhombohedral hexalayer graphene. A lot of and try to use transport measurement to explore the phase space and identify the interesting physics that come out of it. And so this is a 6-layer graphene rhombohedral phase diagram at low temperature. It's not a complete phase diagram. This is focusing around d equals 0, right? And I'm measuring something that's like longitudinal resistance. I'll talk about that more in a second. The point of showing this really is that the transport response is highly symmetric around d equals 0, right? We tried to make the sample without alignment, and I think we got a sample that doesn't have alignment. Right? So in this sample, there's no moire. And what we want to do is to go to the large d limit where we can explore similar physics than what Lang reported. This is a figure taken from Lang where at the large d limit, there's this branch that juts out from charge neutrality point, and all these through hunting phase that shows up. And one of these is supposed to be chiron. Okay, so this is the optical image of the sample that we're using. It has a disc shape in the channel and a contact, right? You can think of it schematically like this. And the sample allow us to source a current, drain it out, right? When you do this kind of measurement, it's something we call parallel resistance. It's similar to longitudinal resistance. But with this configuration, you can change the direction of current flow and do the same kind of R parallel measurement, right? That give you some kind of angle dependence. And so this is the same phase diagram in the large d limit, right? And what the dashed line is circling a region that's that branch that juts out from charge neutrality point. And these are two measurement with orthogonal current flow direction. Right, and the color scale is in log scale, which means that red and blue are several order of magnitude different. Right, so across this region, you can see this very strong anisotropy. And to highlight this, let me take a line cut along this line. Right, so constant density. I'm just going to change displacement field that cut through this region, and this is what it looked like. The red curve is taken along the direction of maximum resistance, and blue curve is taken along the direction of minimum resistance. Right, you can see that there's a ratio of close to 200, and it's actually more clear if I plug it in log scale that in one direction is a resistance minimum, in the other direction is maximum. Right, so we're looking at some kind of very large prominent transport anisotropy. And also let me note that this is 1.5 Kelvin. Right, we're starting at a higher temperature so that the phase space is simple, right? And if you were to park at a constant density and displacement field and look at right, this is very similar to the quantum Hall stripe dimension. And if you were to park at a constant density, right, look at the temperature dependence, this is what it looked like. You can see that the onset of anisotropy roughly starts at about 5 Kelvin, right? And in the log scale, it actually shows that there is some kind of peak structure when you measure along the easy axis, indicative of some type of transition. This is actually a first order transition. I'll show that later. And just to compare with the quantum Hall stripes start to onset usually around 100 millikelvin. Right, so the stripe that we're looking at, or the extreme anisotropy, the order that we're looking at, is much more robust compared to the stripe facing quantum Hall effect region.
Can I ask a question here?
Yeah.
It's Raphael. Why you call this stripe? I mean, you see that there is an anisotropy between X and Y.
Right.
I don't think you can infer from that you were also breaking translational symmetry. I mean, it could be stripe, it could be nematic, but do you have something else that makes you believe these are stripes?
Yeah, so right, you're right. We're looking at extreme anisotropy right now, and I think a little later, I'm gonna show you data where we have the hysteretic melting transition.
So can you just remind us at what density and displacement field this is?
Right. So this is density of from 0.2 to about 1, displacement field from about 800 to 1,000 millivolt per nanometer.
Right.
I will show comparison directly with Long's phase diagram in a minute. This is essentially the same region. Right. So let me be careful with the language. Right. Right now we're looking at extreme transport anisotropy, and we can do more characterization of what's happening here. And the one thing that we rely very heavily on is what we call an extensive angle resolved transport measurement. And this is, we benefit from the collaboration with Oscar and Dimitri, where they essentially figure out a way of doing this, and they taught us how to do it. What they realize is this, that if the electronic order, if the transport response is described by a single conductivity matrix, right, in the linear transport regime, then knowing the matrix, you can fully calculate the potential distribution across the disk-shaped sample as long as you know where the source and the drain is, right? So when you're doing these measurements, you essentially want to map what this potential distribution is, which means that you don't have to be limited to a single configuration that's mimicking longitudinal resistance, right? Instead, you can do any measurement you want. You source at any leads and drain at any other leads and measure between any two voltage configuration, right? All of these, in principle, should be able to fit with a single conductivity matrix. So I think the framework of how to do that is in these two references. I'll just show you what it look like, right? So this is what we call an extensive measurement, and each panel is one configuration, right? The upper left is similar to a longitudinal resistance. Bottom left is transverse, but everything else is kind of some random configuration. And we're fitting all of them with a single conductivity matrix. That's the black solid line that you're looking at, right? As you can see, this is a pretty good fit. And from this fit, we get a ratio between conductivity measured along two principal axes. It's on the order of 1,000. Although there is a big error bar here, because when it gets to an anisotropy ratio of 1,000, the difference between 1,000 and 10,000 is just how sharp this corner is, right? Everything else essentially remain the same. And we don't have enough point around the corner to pin down exactly whether the ratio is 1,000 or 2,000, but we do have enough point. I think this is like close to 100 point to know that we do have very large transport anisotropy, and two, the sample is very uniform, right? If some kind of weird measurement, any weird measurement give you the same conductivity matrix, that means that you really are dealing with a very uniform sample, right? So that's promising, and that allow us to say, okay, let's keep going further to see what we have. Okay, so this is the measurement we did at 1.5 Kelvin. And when you cool down from 1.5 Kelvin to 30 millikelvin, things become more complicated and a little more interesting, right? So we're just gonna focus on this part of this, just this branch, this what we call the, that shows high anisotropy, right? And at 30 millikelvin, the red dashed line is highlighting something that's roughly this branch where we have strong anisotropy. And these are two measurements along the hard axis and the easy axis, right? You can see that generally the strong anisotropy is still there. For example, if you look at this point and that point, right? But a few other things start to develop, including these regimes of superconductivity that has vanishing longitudinal resistance. And we can compare that directly with Long's report, right? In terms of displacement field, it's essentially the same range. And density is also roughly the same range. He marked superconducting 1, 2, 3, right? We have roughly the same structure, superconducting 1, superconducting 2. This one is not fully developed for us, but you can see that it's there, right? And There's a few other metallic pocket that you can kind of see there, which they didn't go into, but we're gonna get to what this is as well, right? So the superconducting phase, right, that corresponds to this one, has a very interesting response. It shows up when we flow current along the easy axis, but it doesn't show up when they flow current along the hard axis, right? So if we were to park here and look at the temperature dependence, but measure along with different current flow direction, then this is what we get. The black curve is measured along the easy axis. There are several that's in the intermediate. They also drop to zero because if you remember the angular dependence we were looking at, right? Let me just back out here. The expected angular dependence has a plateau here, right? Which means that even if you have a very strong, well-defined anisotropy, when the current flow direction is deviating from the anisotropy by about 10 degrees, you still get this vanishing resistance. This is not zero. This is in the metallic phase, but there's a plateau, and that plateau is probably what we're seeing here. But most interestingly, when you flow current along the hard axis, right, orthogonal to the easy axis, the transport response remains highly resistive, even down to the lowest temperature, right? This is actually a very robust response that you're not limited to this configuration. There's also a plateau. Even if you change the current a little bit around this hard axis, you still see this resistive response. It also doesn't depend on what contact you measure with, right? As far as we know, this transport anisotropy, the superconducting phase, is a fairly robust response characterization of the superconducting. Okay, so apart from the anisotropy, the superconducting phase shows a lot of features that's very similar to the chiral superconductor long reported. For example, if we park in the superconducting phase, flow current along the easy axis, right? And this is the longitudinal measurement. We're measuring along the easy axis, and the bottom panels are measuring along the hard axis. When you move the magnetic field, out of plane magnetic field back and forth, right, you see these resistance peaks that show up in the transverse channel, and it shows very prominent hysteresis. And this is directly comparable to what long reported, right? The one difference is that when you measure along the easy axis, it doesn't seem to show the same thing, right? There's very strong anisotropy in the hysteresis. And according to, if we adopt the same picture that long has, that the peaks indicates how the domain boundary is between the two voltage leads, then in this system, what it suggests is that the domain boundary is also aligned along the easy axis, right? Which is kind of quite interesting. And then come to Raphael's question, right? With such extreme anisotropy, the first thing, the one possible ground state is some kind of stripe order. And with transport measurement, unfortunately, we cannot directly see the stripe order. So what we try to do is to look at the temperature dependence, right? See if we can identify a melting transition that's first order. If there's a first order transition, there should be strong temperature hysteresis, right? So this is two measurement that's measured with current flowing along the hard axis. Top panel is measured along the hard axis. Bottom panel is the transverse measurement, right? So this is measuring along the easy axis. So you can see this very large anisotropy again, but most importantly, depending on whether you're cooling or warming, both of them show very prominent hysteresis at low temperature, right? So the peak usually is, people associate that with a pneumatic transition. Above this peak, the anisotropy follow Curie-Weiss law. Interestingly, below this pneumatic transition, the hysteresis appears somewhere else, and we call this T-stripe. On warming, this is where the stripe disappear, and when the stripe start to appear somewhere here, right? There's a hysteresis. And very interestingly, the same hysteresis, or where the stripe appear in temperature, defined by this temperature hysteresis loop, is connected to where superconductivity appears, right? And the pneumatic transition is connected to the temperature where we start to see anomalous hole, right? So there seems to be a hierarchy here where the pneumatic transition is connected to where the quarter metals start to appear, and the stripe and superconductivity always seem to appear at the same time, right? And so if we do the same temperature hysteresis measurement, but now flowing current along the EZ axis, right, you can see this very clear temperature hysteresis, and both on warming and cooling, the superconducting transition seem to be connected to the stripe transition. Right. So this is one of the main reasons that we think we have a stripe phase that has first order melting transition, but at the same time, as over some part of the phase space, this stripe order also give rise to a superconducting phase. The superconductor inherit the same extreme anisotropy, right? So that we can only see superconducting transport behavior very near the EZ axis. That's the orientation of the stripe. Okay, there's something more we can say about the stripe. If it's a stripe, right? If we look at the transport anisotropy as a function of outer plane magnetic field, this extreme transport anisotropy gets suppressed really fast. At the b equals 0, we have a anisotropy ratio about 1,000. And with error bar, this error bar is defined by how sharp the corner is, right? But by the time you get to 0.5 Tesla, right, the anisotropy ratio is suppressed by orders of magnitude. And in this region, the error bar is actually very small, because once we have once the anisotropy becomes weak, the transport measurement is very efficient in determining what the ratio is. Okay, so this transition itself is very interesting, and it turns out that once you turn on a perpendicular magnetic field, the behaves very differently. And okay, I think I have some type. Right, so to see what happens, we'll take a line cut across this line. Right, so we're cutting through a little bit of the superconductor, but also some of these pockets. And if you were to measure density B dependence, right, the left panel is longitudinal resistance, and the right panel is the hole resistance. And this small pocket is cutting through the superconductor. This is not cutting through the most robust part of it, but it gives a very good representation that this superconductor is not robust against a large outer plane magnetic field. It's stable up to about 0.1 Tesla, which is also remarkable for a 2D superconductor, right? But it definitely doesn't go into the quantum Hall effect region. Whereas this metallic pocket that I highlighted at b equals 0, it might be, you could question why I put this dash line here. But once you turn on the magnetic field, right, it's very clear that there's some kind of different behavior showing up. I'm outlining this with a black dash line. And within this black dash line, we see signature of integer quantum Hall effect, right? You almost look like there's a new Landau fan that wants to appear that's distinct from the Landau fan coming from the charge and track point. Okay, so to see what this is, we can take a line trace across these two red and blue bars, right, that cut through two of these quite unique quantum Hall effect state. And what I'm doing here is that the top two panel, I'm plotting line trace measured at 6 Tesla, and the bottom two panel is line trace measured from 4.3 Tesla. If you start from low density, right, you see a number of integer quantum Hall effect occupying every integer plateau, right? I'm plotting sigma xy and sigma xx. For each of these sigma x's vanishes, right? These are very well developed integer quantum Hall effect. This is a Landau fan that comes from the charge and track point. And the vertical dash line is showing you the boundary of of that pocket that I was highlighting. And on the high density side of the pocket, there's a re-entering plateau, right? Whole conductivity re-enters into plateau 4, even though that there's already a few interior plateaus in between. At the same time, longitudinal conductivity dropped to 0, right? So this is very consistent with a re-entering integer quantum Hall effect. And there are multiple of them, right? At 4.3 Tesla, there's a different re-entering plateau that re-enters to plateau value of 5. So the temperature dependence really shows that how different these states are. For a integer quantum Hall effect from coming from charge to point, this is what the temperature dependence look like, right? The longitudinal resistance shows some kind of gradual onset that's essentially a activated behavior, whereas the Hall resistance almost doesn't change, which makes sense because it's reflecting the underlying free charge carrier, which doesn't change as a function of temperature. But if you were to look at the temperature dependence here, right, there's a very sharp onset in the Hall resistance. It goes from a different value at high temperature to this re-entrant value. And at the same time, RxX shows this one non-monotonic behavior, 2 with a very sharp peak. And so if we were to adopt the same picture of the quantum Hall effect from a solid, this is some type of a bubble phase, and this peak is the melting transition, right? And the reason,
Leo, so you have 5 minutes to the question period.
Sorry, what's the question?
So you have 5 minutes to the question.
Unlock your iPhone first.
Period.
Sorry, say again.
5 minutes.
Oh, I see. Okay. Let me just quickly go through the next couple of slides then. Right. So another interesting thing is that at the low density side, right, there is a very large enhancement in the conductivity. And that's actually indicative of an emergence of a superconducting phase, right? And if we were to move the displacement field a little bit within the same pocket, right, you can see the superconducting phase that's next to these re-entrant interior quantum Hall effect state. It has fairly sharply defined temperature dependence. Most interestingly, the transition temperature of the superconducting phase seemed to match the transition temperature of the melting temperature of this bubble phase, right? The transition temperature of the re-entrant quantum Hall effect. And they are about staying over a very large range of magnetic field, right? So our understanding is that there's a hierarchy of different phenomena here. At highest temperature, about 1.5 Kelvin, you start to have a quarter metal phase. And as you cool down in this region, you start to develop this stripe charge density wave at about 1.2 Kelvin. And when you increase an outer plane magnetic field, stripe gets suppressed and a bubble-like charge density wave start to appear. And this phase is stable at about 0.5 Kelvin, right? The stripe phase has its own superconducting phase that also gets suppressed by a large outer plane magnetic field. But once you go into the bubble region, right, you can add the itinerary electron stabilize a different superconducting phase. If you add more itinerary electron, right, that shows up as this re-entering into your quantum Hall effect state. Okay, so that's all I want to talk about. There's a lot of different discovery, observation, and we're trying to understand. We're trying to understand are and what kind of new experiment, what kind of new probe we can use to expand these understanding. Let me skip that and just acknowledge students who did the work and also amazing collaborators that gave ideas that made these possible. The work is mostly done by Ron Nguyen, Aaron Morissette, Pei Qing, and James Zhang, also H.T. Wu. And I benefit a lot from talking with Dima Feldman, as well as Oscar Buffett and all these other people. Okay, thank you for listening, and I'll take the questions you may have.
Okay, thank you for a very interesting talk. So, questions?
Hi, it's Rafael again. I was just wondering, is it obvious to you when you have a stripe phase that when you start changing the current paths by, using different contacts, why the stripe like remains robust in some sense? Why, it doesn't rotate with the, I think this is a question that in the quantum Hall problem was discussed quite a bit. I was just curious to know. And if I can also ask a second question is, did you have any measurement of the in-plane magnetic field? Because that's another way where people look a lot at these anisotropies. And anyway, so I just wanted to hear from you about this too.
Right. So with that angle-dependent measurement, we're using 1 nanoamp, which is extremely small. But when we increase that DC current, right, when it gets to about 10 to 20 nanoamp, that anisotropy gets suppressed by orders of magnitude. I don't think I have that figure here, but when you apply a current that's slightly misaligned from the stripe, you can see the anisotropy start to decrease at about 10, 20 nanoamp. So we thought about probably there are two possibilities. One is that this current is rotating the stripe. The second possibility is that the Joule heating is just melting the stripe, right? And we haven't figured out exactly what to allow us to differentiate between these two scenarios. But I think you're right that a large current does essentially destroy the stripe in one way or another. And another question is about in-plane magnetic field. Have it yet. The main reason is because in plane there's also this anisotropy that in order to do a full in plane measurement, we will need a vector magnet that we don't have yet.
Hi, this is Adi Stern. Two questions or two comments. One is when you have a composite system of superconductor and a metal, when you put a magnetic field, you would get a very strong magnetoresistance just because the current will try to avoid the superconducting islands. So that may be related to the sharp suppression of the anisotropy that you see. The question is, when you diagonalize the conductivity matrix, what are the principal axes? Do they align with the crystal axis or with something you can identify?
Right. For this one, we don't have a good way to identify the principal axis apart from just looking at the straight edges of the flake, and that has a big error bar. So that's a good question that we'd like to look at that next, probably using better second harmonic generation to identify exactly what the axis is. We don't have the information right now.
Hi, great talk. So this is Andre. I have two questions. So the first one is, I think, you're basically claiming that also in long samples in 5 and 4 layers, you'd see similar anisotropy, right? So now you have 4, 5, and 6. What's the TC in these different samples? And then second question, I think that's actually related to Adi, so you probably answered it. If you look at the density where these states appear, is basically the density of where, the flat band sort of, or narrow band appears, right? We can compute it, it's roughly the same. So now we can ask, well, is it some chiral superconductivity on this flat region, but there would be rotationally symmetric, or do I have some pocket physics? But the pocket physics should give you stripes, or should give you stripes, could give you stripes, but only in certain directions given by the pockets and by the trigonal distortion. Do you know if this is compatible to the direction of the stripe, to the pocket, one of the pocket C3 breaking dip?
Right.
Sorry,
Let me answer the first question. In Lang's report, the 4-layer SC1 has a TC that's about 100 to 200 millikelvin, I think on that order. And the 5-layer actually has a suppressed TC, curiously. And in our layer measure along the EZ axis, the TC is around 1 Kelvin. You can probably push it to 1.2 Kelvin depending on how you define it, right? So there seems to be a big jump that we don't know why. So one possibility is that there's similar anisotropy long sample and he's measuring at a random angle. So that could explain why the 5-layer TC actually went down compared to 4-layer. But it is curious that he went through so many samples and never got this situation, unless he's not reporting some sample that didn't work. So I do need to talk to him more, and we are also trying to make 5-layer and 4-layer into the sunflower geometry so we can understand the angular symmetry better. Your second question, I think that makes a lot of sense to us, that there is pocket physics. That's why the anomalous Hall effect and the nematic transition seem to happen at the same time, right? But we don't have strong enough information about the crystal axis. I think that's the main thing right now that prevents us from correlating the principal axis we're seeing to the location of the pocket. We can look at the straight edge, but it doesn't seem to be a very solid way of approaching this. So what we're going to do next is to do second harmonic generation first, and then make the samples so that we know where the crystal orientation is, and then do the angle result measurement to see if the principal axis connected to the crystal axis.
Thanks. But just to follow up, if there's pocket physics, then it's not very easy to get, if I have a stripe, to get chiral, right? To get K plus IK, right? So it's kind of, if there's pocket physics, we know the pocket physics in other regimes don't give you chiral superconductivity, right? So it's very, very puzzling. Thank you.
Hello, Leo. This is Cyprian. I wanted to ask you, your superconductor has some non-zero residual resistance, and I was interested in knowing whether this value is similar if you were to compare it to the if you were to change it to irresistivity, to the residual irresistivity that other groups have seen in the superconducting rhombohedral samples.
Right. So there are two parts to this, right? For the zero field superconductor, we essentially don't see residual resistance, in the sense that here you see the bar. Right? This is essentially half the noise bar that goes to a little less than 10 ohm. Right? So the noise band is about on the order of 7 or 8 ohm, and zero is essentially right in the middle of the noise bar. When you deviate a little bit, yeah, there's starting to be a little bit of residual resistance, but right now you're flowing current not quite along the stripe. So I feel like I'm okay with that, meaning that there might be some physical origin for this noise, not residual resistance. What is really intriguing is this superconductor at the large outer plane magnetic field, right? The transfers, the whole resistance dropped to zero, and this is very close to zero, but the resistance always has a residual here. And I have a to make sense, when we start to see those fragile fractional quantum Hall effect state, right? It's easy to get RxY to plateau, but it's always hard to get RxS to be fully zero. And the reason is that to get RxY to be zero, you need the edge state to fully equilibrate with the metal, which is just hard in the quantum Hall effect region when the sample is small. And I think it's related to the same issue that Long had when he had the fractional Chern insulators, where RxY plateau, but Rx doesn't drop to zero, right? And the solution is highlighted by one of Andrea's recent work. He kind of argued that you just need to make some trenches to enhance the equilibration between the edge state and the metal. And that's what we're going to try next. I think you should help. I get a feeling that that's what it is. But I think it's a good point that the RxS does not fully go to zero, although RxY is, the noise band is within zero, right? So, yeah.
Hi, Leo, it's Oscar. Is there a way to say something about the mini pockets from the frequencies of the Shubnikov that has oscillations?
Right. No, that's a great question. That there's no Shubnikov oscillation within this region, right? I've asked Long the same. They don't see oscillation in this branch. You can only measure oscillation outside of the branch and try to infer what is happening. Although recently we're trying to look at this one feature that's very interesting, that at 1.5 Kelvin, when you look at this stripe region, there is this transport feature that shows up that has some hysteresis right next to it. Right, it could be some kind of Van Hoff singularity, and it's interesting because as you cool down in temperature, this feature moves and cuts across the stripe, and that's where all of these different phases show up, right? So I think I had some conversation with people from Andre's group, but it seemed like a very difficult question to pin down without a lot of experimental input. So that's also my question for all of the theorists here is what other things we can do without the Shubnikov oscillation to understand the pocket physics better. Hello.
Can you hear me now? Yeah, sorry.
Yes.
Can you say something from nonlinear transport about the orientation of the pockets?
Right. Yeah. So the issue within the stripe region, it's a little difficult because that we actually did a lot of DC current dependence, but once you get to about 5 to 10 nanoamp, the nonlinear transport jumps all over the place. There's a lot of hysteretic switching. We have some data that seems systematic, but we don't understand.
So, but how about doing that either at high temperature or at higher density, just to fix the crystalline directions?
Right. Yeah. No. That's a great idea that we could do that. Yes.
So you showed the superconductor that comes in between two different quantum Hall states. Does the magnetic field where it comes in vary with the density? And if so, how?
Yes. Okay, great. So all of these maps, I'm showing you a constant displacement field MB map, right? And I think the question you're asking is this: at different magnetic field, this is the ND sweep at a constant B, and the white dash line is showing the regime of this bubble phase, right? And you can see that it shifts as a function when you change outer plane magnetic field. this pocket shift in both density and also D, right? It goes from upper left to lower right. The shift in N, I think, is indicative of some kind of non-trivial topology, and the shift in D probably is indicative of some kind of a, you change the band structure a little bit, and all of these start to shift accordingly. And so based on this, the superconducting pocket, which is on this side, right, and also the re-entry interior quantum Hall effect, they all shift in both density and displacement field.
So the question that drove my question is, could there be a geometric effect between the cyclotron radius of the electrons at the Fermi energy in the normal stripe and the width of the stripe, which drives this transition between quantum Hall to superconductor and back to quantum Hall?
Right. So the stripe essentially disappears before you get to 1 Tesla. The transport anisotropy becomes single digit, right? And so all of these that we're seeing, I think, is independent of stripe. There might be, probably there's some kind of bubble phase left over, but I think someone, Dima, mentioned something about how the bubble can develop out of stripe, and so it's not. Yeah, there is still an electron solid. And your question about the cyclotron frequency, we don't know.
Cyclotron radius. The cyclotron radius. So
right.
So what I'm thinking about is a geometric effect.
Right. Yeah. No, the question I don't know the answer of. What I do know is that the number of electrons in the solid phase changes with both B and D. A good way. So as a result, the cyclotron, the lattice constant of the solid is not a constant, right? As a result, that straight up slope doesn't work. Straight up slope is a mismatch from the quantum Hall plateau, and it also makes it extra harder for us to identify what is the spatial periodicity and compare that with the cyclotron radius.
Last question.
Hi, it's Andre again. So let me just ask you, for the one that you identify as the chiral superconductor, so the one that appears first in displacement field,
yeah.
Do you have, what's the hard evidence that there even are pockets, right? So the pockets are suppressed in the conduction band by the displacement field, and then they appear at some very large displacement field, right? So maybe the second one. So and the density, if I just look at the density, is roughly the density without any pockets, right? The density range. Right. So what's the hard evidence that there are pockets, or there isn't just a flat bottom?
Right.
I mean, as you know very well, when you put moiré on it, it's the same density, the same region.
Yeah.
And that all the theories on the other side are basically with flat bottom rather than pockets on the moiré.
Right. So yeah, we do have another set of measurement I forgot to add in here, that we did nonlinear transport as a function of temperature, essentially along this line. And we see one-fold angular dependence in the nonlinear response, and that has a very sharp onset essentially at this point, right? So when you start to have an almost Hall effect and go through the cinematic transition, nonlinear response also onset. But then we realized when you have strong linear anisotropy, it essentially becomes impossible for you to extract the nonlinear Hall coefficient based on Oscar's theory. So all we know is that we have some kind of nonlinear response. So I guess that indicates that inversion symmetry is broken right at this point. But apart from that, that's very indirect itself. Apart from that, I don't think we have any direct evidence saying that there's pocket physics.
Okay, so let's thank Leo again.
Thank you.
And let's give ourselves 5 minutes so